Something very much related to third variables and how they can fool us in an analysis is Simpson's paradox. Let me illustrate with the most famous example probably about it. So this is data from the University of Berkeley in California, and this is from the 1970s. And they were studying what was the relationship between the sex of the applicants to the departments of the university. Uh, they were applying for the job basically, and the admission rate. So we have here men and women, and we see that men were admitted 44% of the times. So 44% of the men who applied were admitted, and 35% of the women were admitted. So in principle, we could say that there's a certain discrimination here, and that's what actually happened decades ago. And someone started looking into the data with more detail, and what they found is that, well, it's not so clear. If we look at the data by department, so we have different departments here from A to F, and we look at applications from one to the other, we see that in some cases, men were admitted more often, like in this case, 37% versus 34. But there were other cases in which it was the other way around. So there were women in this case, 82% versus 62%. So on average, it looks like there is an issue. If we look by department, it doesn't look so much. And so this is what's called Simpson's paradox, because there was this person, Simpson, who looked into this and came up with the idea of the paradox. So what Simpson's paradox tells us is that there might be cases in which an effect that is observed at the level of the whole data. If we look into different subgroups of the data, in this case for the department, that effect might disappear or even be reversed if we look at different subgroups. And the point is that it implies there is this third variable that we could group by, so that we could separate the data, split the data into different groups according to this other variable. And that is a variable that might be even unknown to us, or that we cannot have a control over. And in this case, it was just a department. And so what we saw in this data is that the university-wide effect of admission rates per women and men do not hold at the department level. There are some cases in which it is the other way around. And why did we observe that at the group level? It was basically because women tended to apply to departments in which it was more difficult to get in the first place. So they were more often applying to hard departments. And that's why overall it looks like there was this discrimination. So the assumption here, when just looking at the global data at the group level, was that everything depended on the main factor, on men versus women, that everything else was just the same. And sure, if the admission rate was the same by departments and we had the same amount of applications, men and women by department, sure, we can just look at the aggregates. But if it's not, like in this case, and 99% of the times it's not, then we have to be careful with this. It was just, again, in this case, that women tended to apply to harder departments. And that's why overall we saw this effect. There's plenty of other examples of this. There's another one that has to do with kidney stones. And in this case, we have two treatments, A and B. One is invasive and the other one is non-invasive. If we look at the success rate, we see that treatment B, the non-invasive, is successful in 83% of the cases. And in this situation, you see we have 350 patients in both treatments. So 83% of the times it's successful, the non-invasive one. So one would say, why bother with the invasive one if the other one was better, right? Again, it depends. And the third variable to take into consideration here was the size of the stones. So what we had in this data is that patients with small stones were more often assigned the non-invasive treatment. So we have here 270 versus 87. And people with large stones, they were not bothered with the non-invasive treatment. They were all ready for the invasive one, 263 versus 80. And then in here, if we look at these specific groups, what we see is that in both cases, both small and both large, the best treatment was treatment A. So again, this effect that we observed at the group level, 83% success rate versus 78, is reversed when we look at the subgroups, because there's this third variable, in this case, the size of the stones, that is actually the one making a difference. It's not just treatment A or B, it's the size of the stones. And so when the less effective treatment is applied more frequently to less severe cases, it could appear that it's more successful, but it's actually not. Another one is from, again, a study years ago on survival rate by smokers versus non-smokers. So they studied different people for 20 years, and after those 20 years, they saw whether they were still alive or not, and whether they smoked or not. And what they found is that people who smoked had a mortality rate of 24%, but people who did not smoke had a mortality rate of 31%. So in principle, one could be inclined of saying, hey, start smoking because you're going to last longer. We nowadays, of course, know that this is completely stupid. There has to be something out there. And there is. The third variable was actually the age of the subjects. So the problem was that the group of non-smokers had an overrepresentation of elderly. So if we look at the bar plots over here, we see that the red one, non-smokers, had a very large number of elderly and also people between 65 and 74. Whereas in the smoker case, there were a lot of people here in their 40s, 50s. And so the problem was, of course, that just because of their age, in the non-smoker group, there were more people that were going to die in this 20-year period, just because they were older, not because they were non-smokers. And so if we look at per group, in this case, per age group, we see that smokers actually tended to die more often. So we here have smokers, again, in this green and blue, and the percentage of them who survived, we see it's always less than in the red group of non-smokers. So the third variable in here was the age, which you see, it's not categorical. It could be, we could have Simpson's paradox between categorical and numerical variables all the same. And even numerical and numerical. So another example we have here is data about cell phones, and what we have in the x-axis is the price of the phone, and what we have in the y-axis is the demand, so how many units are being sold, essentially. Now, according to economic theory, if the price goes up, the demand should go down. And what we see here is that there's basically no such relationship, or it could be even be reversed. There's this slight positive correlation. So this does not follow the rules of economic theory, right? It actually turns out that it depends on time. So if we plot both of them, the quantity demanded here in blue and the price in red, what we see is that there is this relationship with time. And here we're measuring time in terms of weeks since the product came to the market. And so we see that both variables are actually very much correlated, and they go down with time. And of course, we see these peaks for holidays, etc., that the prices tend to go up. But anyway, so there is this relationship between both of them, but it's just having the effect of the time. So what we could do is, for example, instead of looking at data from all weeks over here, split the time in different groups. So for example, weeks 1 to 75, 76 to 125, and beyond that. And if we plot the data only within these groups, we see that there is indeed this negative correlation between the price of the phone and the demand for the phone. So this is a case in which Simpson's paradox is also at play, in which the relationship between these two numerical variables, price and quantity, depends on another numerical variable, which is the time. And the second paradox I want to tell you about is the inspection paradox. We can best illustrate with an example. Let's say you're interested in how long do people wait for the train. And we have two options here. We could just go to the logs of the station and see what was the time between trains. I'm sure there are logs of that every day. We could just go there, measure, compute the average. Let's say that it's 5 minutes. And then the second option is we could just go there and ask the passengers, how long did you wait today? How long did you wait yesterday, etc. And it turns out that if we actually do that, the average is 6 minutes. So we have these two different studies that are trying to measure the same thing. What is the average time between trains? They're giving us different responses, different answers, 5 or 6 minutes. In principle, both of them are okay, but option two is not. And here's why. In the plot, we have the actual distributions of real time. So we see that the ones in black go every 10 minutes. And so that means on average, we wait half that, 5 minutes. But if we ask people, then the distribution is shifted towards the right. And they tell us it's 12 minutes between trains. So they have to wait on average 6 minutes. Now, why is that? Why do we have different answers? Well, it's because of the inspection paradox. The thing is that each member of a population, in here the time between two consecutive trains, is sampled proportional to its size. What that means is the probability of observing a certain quantity is related to the quantity itself. In the case of the trains, our arrival to a platform is a random event, just like the train's arrival. And it just happens that we are more likely to arrive at a longer interval, well, because it's longer. So let's say that each of these points represents the arrival of one train. So between those two, it's 7 minutes apart. Between the next two is 10 minutes, 5, 12, and 10. Then we are more likely to arrive at a long interval of 12 minutes because it's longer. We could arrive here, 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 etc. It's just longer. It's less likely that we arrive at an interval of 5 minutes because it's shorter. And so more often we are going to come to this interval, and that one turns to be long. And so when we report how long did we wait on average, we're going to wait longer because we arrive at this longer interval. If we arrive at this one, we're going to say we didn't wait that much, but it's very unlikely that we arrive at the 5-minute interval because it's smaller. So the inspection paradox in this case is fooling us into believing that we wait on average 6 minutes when in reality it's only 5. We can look at the actual data, the actual times, looking at the station's log, and we see it's 5 times. If we ask people, it's going to be 6 minutes because we have this paradox being play. It could also happen that we measure certain quantities about groups, but instead of sampling the groups, we sample their members. Let me show you an example. Let's say that we are interested in the average number of students in a school, so average number of students per class. Option one, we go at the school registry and we actually look at the real numbers. Let's say that we have 3 classrooms and it's 20, 60, and 100. So the average is 60. Second option is we just wait outside school and ask the students. 78. We have a very clear difference in here, 60 to 78. And the point again is we are not really measuring at the level that we should be measuring, because we should be measuring these 3 numbers, 20, 60, and 100. That's what interests us, the class. If we study the members of the class, so in this case, the 20 students, the 60 students, and the 100 students, then it's more likely that we sample more in this class than in this other class because it's larger. And so the actual answer here, the real answer is 60 over there. But here in red, we have the distribution of what would be expected of the second study if we ask 50 students. On average, they would tell us it's about 78. Anywhere between, say, 65 and 90, those are possible answers. But those are wrong because we are asking the students and we are not asking the classrooms. Those are different things. So this is again another case in which the inspection paradox might fool us if we do not sample correctly the data.